last longer than others. Some are good commercials and they last longer, some are not. So we need a guidepost, and that's what these information criteria are. Is this a pain in the butt? Absolutely, but it's all we got. So we set it on 18. Here's our model. Lags from 0, and 0 meaning current freezing days in this month, to previous freezing days. And notice that not all of them are positive, because freezing days should increase the price. Some of them go negative. But remember that thing we talked about earlier, multicollinearity. Multicollinearity screws up everything. It not only screws up your t-stats, it also screws up your coefficients. So a lot of this can be due to what we're calling multicollinearity. Just the fact that all of those coefficients are probably highly correlated with each other, and that just kind of screws up with the regression process. It makes it hard for us to tell which results make sense and which ones don't. All right. Save that, predict it. Let's see here. We can barely see what's going on here. But the blue is the change in price, and the red are the fitted values. This is not a very good graph. All right. So remember what we said. Oh, we can do Granger causality. Let's do Granger causality. So Granger causality measures what is the effect of our freezing days independent of whatever trend might be happening with prices. Right? Is that kind of how we put it? So we had price changes are dependent variable, and then lag price changes. So if price changes are just following a trend, then all of these should provide the explanatory power. Now we want to see if freezing days contributes anything. And so we include current freezing days as well as lagged freezing days. And then we're going to test to see if all of these, not individually, we could see this one's significant, significant, not significant, and so on. So we're not going to test them individually, we're going to test them jointly. Are all of those jointly significant? And that's an F test. And so we have to set L1 equal to L2 equal to L3 equal to L4, blah, 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 and test if they're jointly significant. And it turns out, Stata's got an app for that. There it is. Our test parm function constructs an F test. So test parm is for test parameters. And which parameters? Test our lag values from 1 through 18 of our price change variable. So this is testing to see if the betas, the lag values of price changes, are jointly significant. So remember, the null hypothesis is that they're not significant. The alternative is that they are significant. So we get an F-stat of about 1.86, and we know how to interpret a p-value. So our p-value, remember, smaller p-values are better. So this is about 0.01 or 0.02, so we could say this would be significant at a 5% level, which is a standard p-value. We can do this for freezing days also. So what this tells us is, our first result, what this tells us is that price changes do follow a long-term trend, and that past price changes are a good predictor of future price changes. So this is saying that yes, price changes are following a long-term trend. Now, we're going to test freezing days. Do freezing days add any explanatory power? And again, we got an F value of 4 and a P value of 0. Is that good or bad? P value? It's good. Does it mean freezing days has explanatory power or doesn't have explanatory power? Doesn't? So the null hypothesis is that freezing days don't have any explanatory power. The alternative hypothesis is that they do. So we're rejecting the null and concluding that freezing days do exert an effect on the price of frozen orange juice. So this is good for freezing.
Less than 5?
Yeah, it's less than 0.05.
0.05.
Yeah. Coming back. So 0 is good.
And that's the P value.
For the P value.
bottom one.
Yeah.
And what does the top one mean?
It's the F statistic. It's kind of like a T statistic, but it's for a joint test. So when we do individual tests of significance, we're testing coefficients. Those are T tests. So when we go to the regression, those are T statistics. But when we do a joint test, so for anyone, for example, for lag 18, its T is small, its P is large, so this is non-significant. But when we want to test all these together and say, look, we're not going to test anyone individually, we're going to say jointly, do they have any explanatory power? Then we have an F of 4 and a P of 0. So we would reject the null, conclude that freezing days do have an effect on the price of orange juice. At least as measured by Granger causality. And this is the Granger test. So freezing days do Granger cause.
Is your null hypothesis always that there is not going to be an effect?
In this class here. All right. Now let's get to the hard part. I'm joking. All right, I'm just running the regression so we got that. Remember what we want to do. We want to graph these coefficients. These coefficients represent the effect of freezing days on orange juice prices, frozen orange juice prices. We want to graph them, which means we have to save them and then graph them as a function of their lag. So what we want to do is, we have that picture. What we want to do, right, 1 period ago, the effect was that. 2 periods ago, the effect was that. 3 periods. So we want to graph the coefficients as a function of their lag. So we don't have a variable called lag, but we're going to create one. And essentially, we just need something that goes from 0 to whatever. This is going to go from 0 to 641. But we're not going to use all those. We're going to use 0 to 20, because that's all the lags we have. So what I did was just, did everybody see that? Oops. Generate lag equals underscore n, which is just going to create a linear sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then I'm going to subtract it from 1 so that I have 0 in there. So underscore n minus 1 will create 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Then we need to save those coefficients. I need to pull those coefficients out and so I can grab them. And if you remember, so display underscore b, do you remember that? Vaguely? Square bracket, and then L1 dot This is the beta coefficient, and this is the coefficient we want to display. So to pull out that coefficient, we use this underscore b with the square brackets, and those are square brackets, and that's the coefficient. What we're going to do is save a variable of those coefficients. Save those coefficients. With something like this. So I'm going to call my lag betas L beta for lag beta. What does it equal? It equals the coefficient on freezing days if lag equals 0. So this is the current effect of freezing days on orange juice prices. You see that? Then I want to redo this, but I want to do it for a 1 period lag and then a 2 period lag. So replace L beta equals lag 1 freezing days if lag equals 1. And here's the nice thing. Once we got this replaced down, then you go down and you change this to 2 and that to 2. 3, 4, 5, 6, 7, right? You just change those numbers so that you're following those. And as you can see, that's exactly what I did. Now, I've got the two things I want to graph. I got my lag, and I got my L beta, my coefficient, my regression coefficient. And I'm just going to scatter those suckers. There it is. If we go to our regression, we'll see that these values here, I think the first one was 0.47, and I think the second one for the 1 period lag was 0.17, I think. Let me go back to the regression. Let's go up. Yeah. So first one was 0.49, the second one was 0.47. So basically we're graphing our coefficient results. This is how you show, we're going to do this for sales and advertising. This is how you show the effect of advertising over time of current and past advertising expenditures. And that's your picture. The effect of freezing days over time of past freezing days. So essentially you can say one of two things. Right? 8 periods ago, the effect of freezing days was, well, let's say 4 periods ago, the effect of freezing days was here. Whatever that is. It's statistically insignificant, but it's there. So, again, 4 periods ago, the effect on prices today is here. Or you could say a freezing day today will have effect of this in 4 days. So you're basically saying the same thing. All right. Is that kind of a pain? All right. You thought that was a pain. What do you see this? We're going to want to construct a confidence interval around that. And if you remember what a confidence interval was, we take, well, in essence, here's the confidence interval here. around this value. So the confidence interval is in here. You just have to pull it out. It's kind of a pain. But I actually did it by hand because we have to give it a T-tail. This is a real pain. Yeah. So, what did I do? For freezing days, I subtracted the standard error, multiplied it by times the t, and then I added the standard error and multiplied it times the t to give us that 95% confidence interval. If you see, those values should coincide with be able to reach it, but look at the first coefficient, freezing days. Coefficient of 0.49, go all the way over. The lower confidence interval is 0.37, and the upper confidence interval is 0.607, and that's what we did here. That's how you calculate these. You've got to do that for every one of those coefficients. And again, copy and paste is your friend. So I'm going to generate lower confidence interval, which is, and the upper confidence interval. And again, you can just see the lower confidence interval, I'm subtracting the margin of error. The upper confidence interval, I'm adding the margin of error. So let's see, where does it start? All right. So generate lower confidence interval. My coefficient, the margin of error is the standard error, underscore standard error. So it knows to pull the standard error from the regression output, and then we're multiplying it times this t. This t is the sample size, the degrees of freedom, which we get from the model. So 604 is our degrees of freedom, which we get from our regression model, which is right here. It's the degrees of freedom of our residual. So again, it's really a copy and paste job. Generate that first one, replace, and then you change your lags in your standard errors in here. 9, 8, 7, 6, 10, 11. So copy, paste, copy, paste, copy, paste, copy, paste. So we're doing all of this to get one picture. Which is that picture. Again, this is freezing days, but what we're going to do is you're going to do the effect of lag advertising on sales, so we can see if the effect of the lags looks something like this. Now, let's go back a little bit to before we started this. This is actually pretty interesting. If the lag looks something like this, remember we had those two models, we had the bubble, parabola, and we had the geometric decay. If the lag looks something like this, which model might we apply to this lag? Exactly. In fact, this looks like big increase, geometrically decays pretty quickly. The effect of advertising has an initial effect, and then it starts to die out. And this is exactly what we're going to be doing. If the lagged effects had that more bubbly look, where the coefficient kind of rose and then fell, then we'd use that parabolic function. So this is what I mean by, we're going to let the data tell us how to impose some structure on these lag coefficients. First step is this. What do those lag coefficients look like? Does it give us a hint as to how we want, or how we should model the effect, these effects? And the answer in this case, I think, is a pretty obvious, that looks like geometric decay to me. So that's what we're gonna do. The nice thing about geometric decay is we're gonna get, and think about this, you know, behavior, as we said before, usually occurs pretty smoothly. So we're gonna assume that that function dies out at a pretty constant rate. And we're not gonna see these kind of jaggedy effects here. So we're gonna get a really cool picture. But to get that picture, we gotta go through all this stuff. Then we gotta, I mean, think about this. This is just looking at the raw lab coefficients. Then we gotta come up with this geometric decay function and add that to the model. But it'll blow your mind when you do it. It's really, really cool. I've seen this done a handful of times, and I could tell you, I could actually bring you a PowerPoint that basically generated this picture, and the cost was insane. There was more than one slide, but in essence, to get to this one slide, they charged about 350 grand, consulting company. I kid you not. I got it, and I've got the price on it and everything. I've got the PowerPoint stack, and it was sent to me because one of you guys, a former student, said, "Hey, our firm just hired this consulting company to do it. It looks like the geometric decay that you covered in class, and you won't believe what they charged us for." And I looked at it, and he was right. But he knew what it was. He had just gotten there, so they didn't kind of run it by him first. But it blew my mind. I'm like, holy cow.
How many slides? 600 or so?
Yeah, but a lot of it is like busy work. It's a lot of it is like background on the product. Well, you know, kind of some pie charts and all this stuff. But the gist of it was to try to come up with this kind of half-life of advertising. How long does advertising last? When does 90% of it disappear, and all those things? And that was the stuff that they wanted. The other stuff was, like I said, was probably canned stuff that they had from a previous presentation. No, in fact, he told me half of it was stuff that they gave him to include in the presentation. So it was. Now, is that a pain in the butt? Absolutely. Is there an easier way? Perhaps. We can use margins. Remember margins? Margins does everything, but you just have to tell it. So we're running out of time and juice, but we can generate this using margins. So remember that margins is a post-regression command. So there's our regression, and I'm going to use the command margins, comma, dydx, and dydx tells me not to do a prediction, but to just give me the coefficients. So dydx are the coefficients. Star means give me all of them. So if we had specified, like, just give me one or two, we could have said, give me those. But putting the star in there tells me, give me all of the coefficients. Now, the nice thing about margins is that it creates this, gives you all the coefficients, and it gives you the 95% confidence intervals. The cool thing about margins is you can save margins. It'll create a whole separate stated data file of just your margins results. You don't have to go through all those L betas and lags and this and all that stuff. So we can save this output. It's just going to be in another stated file. So do you remember, did we save margins? I doubt it. So the command for saving margins is, guess what?
Save margin.
Save, exactly. Control V. Same command, ignore that. Same exact command. But again, guess what the command for saving margins is? saving, and then tell it where to go. So I'm telling it to go into this file, and I'm going to give it the name I'm going to give it is margins underscore oj.dta, because it's going to be a state of file and comma replace.
Is it always comma replace, or is it like outreg where you only do replace after, or?
You don't have to put it there, but like for today, if I want to redo this, then it'll just replace the old one. So you don't have to put the replace in there. Okay, I'm gonna hit it. It's gonna create a new file. So I don't want to clear out this one, but I'm gonna. What you can do, Stata lets you open up more than one file at a time. So it created the file. I just got to pull it out of my off the flash drive. Massachusetts. Wow. Oh, there it is. We got 40 minutes left. Really doubt that. 10:60. But let's do this. Essentially what you're going to get is this. You're going to get this, these coefficients in this file. These coefficients are going to be called margins, underscore margins. So underscore margins is going to be the stuff that you're trying to get. And then if you type describe, so once you open this up, type describe, and you'll find margins, and you'll find underscore. You'll find a variable that I think is lower confidence interval and upper confidence interval. So it's going to give you, it's actually going to give you all of this, but you want to graph this along with these two things. And that's it. So instead of going through, so you got two options. Go through margins, and you're going to get this in a file, or you go through this code here. This, and then this. So it's up to you. Yeah.
So how would you graph from the
Yeah,
saved
so
margin?
in this you've got scatter margins, scatter this, margins, LCI, UCI, and then you're still going to have to generate lags. Remember lags was underscore n minus 1. So you're going to have to still generate lags because you still want that same graph. So in essence, it's the exact same command that you used for, all right, so here's that. It's literally the exact same command except for, yeah, okay, so here it is. It's literally the exact same command except instead of L beta, remember stated cause this margins, underscore margins. And then, I'm not exactly sure what your lower and upper confidence intervals are called, but they're named in that file. So in that file, there's a name in there, I just don't remember off the top of my head. And then you need to generate lag. And you probably have to put the part here. Other than that, it's all the same stuff. This is the easiest way now. There's probably a way to do it using margins plots, now that I think about it. As nasty as this sounds, and it is nasty, it might not be I know we like to minimize our work, but it might not be that bad of an idea to do this by hand. One, it's copy and paste. It's 18 of them, but it's copy and paste, and then you just change lags and you do all that stuff. It's not as tedious as it appears. It's going to go a lot faster than it appears. Once you get the first two done, then the next 16 will take you a minute. It's literally copy, paste, change the number, copy, paste, change the number, copy, paste, change the number. Let's say it takes you a minute each. It's still only 16 minutes. And it's not going to take you 16 minutes, by the way. And the reason why is because even though margins will do this for us, margins isn't going to be able to do the geometric decay for us. So we need to get used to constructing these kinds of codes so that we can do the geometric decay and the bubble and the parabolic function. This is really cool stuff. It's, like I said, this whole distributed lag model, this is how 99% of the time it's done. Everyone uses distributed lag models because they're easy. They're simple to understand. The problem is kind of what we're seeing here. We've got a bunch of negative coefficients that don't make sense. Almost nothing significant, which doesn't make sense. But we know what that problem is. It's probably this thing called multicollinearity. So what the distributed lag, what the geometric decay model will do and the bubble model will do is allow us to eliminate that multicollinearity and get better results. More reasonable results, but also more telling results. The geometric decay stuff especially is one of my favorite models. So that one's really cool. So like I said, the margins will take you a second to do, but it wouldn't hurt to actually try to go